Hello. Dear students, Assalamu alaikum everyone. There was a technical problem for which I had to leave the meeting and I had to rejoin. So please inform your friends to join. Sorry for the interruption. Hopefully within a minute we can start. Please share the joining link so that other students can join. Dear students, please forward the link. Thank you very much. Dear students, please inform others to join. I'm waiting just a minute. 1 minute only. We'll start the class. Within a minute, inshallah, we'll start the class. Please inform others to join. Okay. Let us begin our class. As we were discussing uh, specimen paper 16, you remember. So first two questions were discussed. From question number 3 we will start our discussion. Question number 3 onward we will start discussing. You can see the screen right now. Have a look at this. This question refers to the elements shown in the portion of the periodic table given below. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. You can see this one. From this table, identify in each case one element that has the property described. Give the symbol of the element in each case. The element that forms the largest cation. So look at this one. From this table, identify in each case one element that has the property described. Give the symbol of the element in each case. You have to give the symbol only. Okay? You have to give the symbol only. The element that forms the largest cation. The largest cation. So here you see, as you go into the right side, the atomic size decreases, right? Atomic size decreases. And as we go down, atomic size increases because every time we are getting a new shell. So the element that forms the largest cation will be potassium. It will be potassium. Let's go to the next one. An element that floats on water and reacts with it. An element that floats on water and reacts with it. So it could be any group 1 element. So it could be sodium, potassium. Next, an element that reacts with water to give a solution that can behave as an oxidizing agent. An element that reacts with water to give a solution that can behave as an oxidizing agent. So first of all, you need to see which elements can react with water and which cannot. And when it reacts with water, it behaves as an oxidizing agent. Okay, so you have to be very careful for this question. So we can think of sodium, potassium. These metals react with water, but what do they form? They form sodium hydroxide and hydrogen. So none of these are oxidizing agent. On the other hand, if you think about chlorine, for example, chlorine can also react with water. So when chlorine reacts with water, at the time, what happens? Chlorine reacts with water, at the time we get hydrochloric acid and hypochlorous acid or chloric acid 1. We get these two substances. So chloric acid 1 kills bacteria because it is an oxidizing agent and it provides oxygen, right? It provides active oxygen which actually kills bacteria. So we have seen that chlorine or bromine can react with water to form oxidizing agent. So here the answer will be chlorine or bromine. Now come to the fourth one, an element in the S block whose nitrate gives a brown gas on thermal decomposition. An element in S block. Now what are S block elements? The element where the last electron enters into S orbital. The last electron enters into S orbital is known as S block element. So lithium, sodium, potassium, beryllium, magnesium, calcium, these are S block element. Now look at the nitrate of lithium, sodium and potassium. What happens at that time? Lithium, sodium and potassium. Lithium, sodium and potassium. You know that lithium nitrate decomposes to form lithium nitrite, group 1 metal nitrate decomposes to form lithium nitrite and oxygen. Lithium is an exception. Every element in the first element of every group, shows exceptional behavior. So lithium is an exception here. Sodium, potassium or other group 1 element like rubidium, their nitrate will decompose. Their nitrate will decompose. The nitrate will decompose to form their nitrite and oxygen. Okay. On the other hand, if you take magnesium nitrate or calcium nitrate, what will happen at the time? They will form the respective oxide. That means they will form magnesium oxide, nitrogen dioxide and oxygen. So nitrogen dioxide is a brown gas. So what will be the answer? Magnesium or calcium, right? Magnesium or calcium. Even lithium can be chosen because lithium has a similar property to magnesium and calcium. There is a diagonal relationship between lithium and magnesium. Similarly, beryllium with aluminum. The first element of group 1 and the second element of group 2 will have a diagonal relationship. First element of group 2 and second element of group 3, that is aluminum, that will have a diagonal relationship. Okay, so this will be the answer. Let's go for the next one. B1, give the formula of the oxide of the most electronegative element. Now, how does the electronegativity changes? How does the electronegativity changes? What is the pattern of change of electronegativity? As we go to the right side of the periodic table, we get more electronegative element. From left to right, we get electronegativity increases, and group 7 elements are the most electronegative. Here, noble gases are excluded. So, group 7 elements are the most electronegative element, right? Group 7. So, it's oxide. And again, if you think about the electronegativity, then what is the trend in electronegativity in group 7? As you go down, electronegativity decreases, right? So, fluorine is the most electronegative element here. Fluorine is the most electronegative element. Fluorine is the most electronegative element. So what will be the formula of its oxide? F2O, right? Then let us go for the next one. Several of these elements form more than one acidic oxide. Okay, can you see my screen right now? Dear students, anybody respond, please? Okay, so look at this one. I have written the answer here. Potassium, you match the answers. Um, give the formula of the oxide of the most electronegative element. So we have given F2O. Then let us come to the next question. Several of these elements form more than one acidic oxide. So you know that non-metals form acidic oxide and metals form basic oxides in general, right? So give the formula of two such oxides formed by the same element. So we can think about sulfur dioxide and sulfur trioxide. We can also think about nitrogen dioxide, nitrogen trioxide, right? So look at this one. I have given sulfur dioxide, sulfur trioxide. So this could be an answer. Next one. Next one. Give the formula of an oxide with a very high melting point used as a ceramic insulator. So formula of an oxide. So which oxides have very high melting point? So let us find out these oxides. It could be magnesium oxide, it could be aluminum oxide, it could be silicon dioxide. Any of this could be given as an answer, but I prefer silicon dioxide. Silicon dioxide is has a giant tetrahedral structure, you know, and it has strong covalent bonds in its tetrahedral network. In its tetrahedral network, it has a very strong covalent bond. So to break it down, we need to provide high temperature. That's why it is a very good insulator and it is used. Next one, next question. Give the next question. Explain these properties of the oxide chosen in 3. So here, except magnesium oxide is completely ionic. Aluminum oxide has slightly moderate character. It has ionic bond, but it has slightly covalent nature in it. On the other hand, silicon dioxide is completely covalent. So one portion you need to mention that it has okay, Hanadi, I am showing the previous question again. Give the formula of an oxide with a very high melting point used as a ceramic insulator. So as an insulator, what can we use? We can use a substance which is resistant to high temperature. It does not break down at high temperature. In your book, I'm giving you a reference. In your book on page number 158, note it down, page 158, everyone. On page 158, you can get to know about this one. Page 158, textbook. Page 158. You can see this page. You will get to know why magnesium oxide is used. Magnesium oxide to line the inside of furnaces because it is resistant to high temperature. On the other hand, aluminum oxide and silicon dioxide to make ceramics with the giant covalent structure designed to withstand high temperatures and provide electrical insulation. So here, what reasons can we write? We can write that they have strong covalent bonds and giant structure. Okay, giant structure. These are the properties which is chosen. Let us see this one. I have written giant structure with strong covalent bonds. So these are the 2 points. One is giant structure, another is strong covalent bonds. So let's go to the next question. I am simultaneously sharing my screen, my PDF file, as well as my image file. I think you can see both simultaneously. Can't you? Can you see it simultaneously? Dear students, please let me know. Let me know, please. Okay, thank you very much. Let's see. Okay, I got it. Now let's see the next question. The formula and the melting points of the fluorides of the elements in period 3, sodium to chlorine, are given in the table. So sodium fluoride, magnesium fluoride, aluminum fluoride, silicon tetrafluoride, phosphorus pentafluoride, sulfur hexafluoride, and chlorine pentafluoride. You can see this one. What is the shape of SF6 molecule? You know that it has an octahedral structure. So I can proceed to the next one. In the sequence of fluorides above, the oxidation number of elements increases from sodium fluoride to sulfur hexafluoride and then falls to ClF5. So this is mysterious. You can notice this one, right? You can easily notice. So chlorine pentafluoride, you can see chlorine pentafluoride. You can see it. I have highlighted this one, chlorine pentafluoride. From sodium fluoride to sulfur hexafluoride, it is increasing, but it should be ClF7. Instead of ClF7, it is becoming ClF5. So that is a big question. Why it is not ClF7? It is ClF5. Attempt to make ClF7 have failed, but IF7 has been prepared. Suggest an explanation for the existence of IF7 and for the non-existence of ClF7. So you see that chlorine is a small atom. Chlorine, when we compare iodine and chlorine is a small atom. So it cannot make a bond with 7 fluorine atom. The space does not suggest to accumulate 7 fluorine atom. Instead, it accumulates 5 fluorine atom. It can only make a bond with 5 fluorine atom. So I have written it here that iodine atom is larger than fluorine atom. Iodine can pack 7 fluorine atoms around it, but chlorine cannot. So that is the answer. I hope you can see it, right? Okay. Look at this. Iodine atom is larger than chlorine atom. Iodine can pack 7 fluorine atoms around it, but chlorine cannot. That's why it doesn't happen. Okay. So let's go back to the question once again. Come to question number 4. Complete the following reaction scheme which starts with propene. So propene, this is an alkene. This is what? An alkene, right? Propene is an alkene. So when you carry out the reaction, the main reaction of alkene is electrophilic addition. And we know that where the reaction will take place. The reaction will take place in carbon-carbon double bond. So here we will have the reaction. The reaction will take place in carbon-carbon double bond only, nowhere else. So what will happen? This double bond will break down and one bromine will be added to this one, another bromine will be added to this one. So we'll get dibromopropane. So in fact we get 1,2-dibromopropane. On the other hand, you see that when we carry out the reaction with potassium dichromate, potassium permanganate, with potassium dichromate we don't get this reaction. Potassium dichromate. Two things are very important here. The condition. Always condition is very important in organic chemistry. You see that when we are using cold dilute potassium permanganate, this is a mild oxidizing agent. This is what? A mild oxidizing agent. Okay. So this one I can write it here, a mild oxidizing agent. It is a mild oxidizing agent. Mild oxidizing agent. So when a mild oxidizing agent reacts with alkene, what happens? With double bond breaks down in both of this carbon having double bond will have OH. So we will get a diol, right? We will simply get a diol. So look at this one. I have shown the product. We are getting a diol when we are using cold dilute acidified potassium permanganate, potassium manganate 7. At that time we are getting diol. Look at this CH. Look at this one. Look at this one. Simply, what is happening with this one? One OH is coming, right? With this one, with this carbon, another OH is coming, right? With this one, another OH is coming. Understood? So this is a diol. But if we carry out this reaction with what is it called? If we carry out this reaction with hot concentrated acidified potassium permanganate, at the time this double bond will be broken down completely. And as you have CH2 in this side, it will turn into carbon dioxide. So let me, if we carry out this reaction in presence of what? In presence of hot acidified, in presence of hot acidified KMnO4, right? If we carry out this reaction with hot acidified KMnO4, at the time what will happen? At the time what will happen? We will get in one side we will get CH3 C double bond OH. That means we will get acetaldehyde in one side. There will be two product, right? There will be two product. One is CH3 CHO, and another product will be carbon dioxide, right? Another product will be carbon dioxide. And you know that further, if we carry out this one, further if we carry out this reaction, this oxidation, further if we carry out this oxidation, what will happen at that time? At the time we can get CH3 C double OH, right? We'll get this one. Understood? Okay, so this is oxidation, this is also oxidation. When you are using cold dilute acidified potassium permanganate, at the time you are getting diol. On the other hand, when you are using hot acidified concentrated potassium permanganate, at the time this double bond breaks down completely. It breaks down completely. What happens? It breaks down completely. This bond breaks down completely at the time. Okay, this bond breaks down completely, and we are getting two different products. One is carbon dioxide, another is CH3CHO, that is aldehyde. From there we get carboxylic acid. Anyways, let's go back to the question. So they were asking what would be the product if cold dilute acidified potassium permanganate is used. So we will get a diol. So here's the diol. I hope you understood. Now the next part, if we use HBr, hydrogen bromide, if we use hydrogen bromide, what will happen? We can get two different products. We can get two different products. One is, you know that addition reaction will take place. So only the double bond will participate in the reaction, nothing else. The double bond will participate in the reaction. Okay. I'll come back to this one once again. Okay. Look at this one. If we carry out the reaction with hydrogen bromide, another addition reaction will take place. CH3CHBr CH3. So that will be the major product. That will be the major product, and another product will form CH3CH2CH2Br. That will be the minor product. Okay, they are asking for the major product in the question. So look at this. They are asking for the major product. So we are writing the major product. I'm going back to the question once again. Major product. Now, why it is happening? I told you a simple tips. You remember? You remember, right? That giving oil to oily head. Giving oil to oily head. For this one, you see, if hydrogen is added to when carbon-carbon double bond is asymmetric, that means both sides does not have the same group attached. When we have different number of hydrogen attached to carbon-carbon double bond, at the time, what we need to do? Look at this. when the carbon-carbon double bond is asymmetric, we know that we use this concept, giving oil to oily head. Okay, remember this one. So where is hydrogen? Hydrogen, more hydrogen is present in this carbon, right? More hydrogen is present in this carbon, isn't it? More hydrogen is present here, so hydrogen will be added here. If hydrogen is added, our product will be CH3, and this carbon has less number of hydrogen, so with this carbon, what will be added? Bromine will be added. So this is how we are getting the major product. Alternatively, you can give hydrogen here and bromine here. So when you give this one, you will get this product, CH3, CH2, CH2Br. That will be a minor product. Understood? Is that clear, my dear students? Okay, I will explain the mechanism after a while. Even I can explain it right now. Look at this. At the bottom, I have written, you know that in electrophilic addition reaction, an intermediate will form, that is carbocation. If the hydrogen is attached here, you know that there was a double bond, right? I'm showing the double bond here. There was a double bond. This double bond breaks down. So when this double bond breaks down, uh, one carbon will have a positive charge and another carbon, hydrogen, will be added from hydrogen bromide. So suppose this carbon is having this hydrogen, so it turns to CH3. From CH2 it turns to CH3, and here what will happen? Here we'll have a positive charge. On the other hand, if the hydrogen is attached to this carbon, another carbon, this one will have a positive charge, right? This one will have a positive charge. Now when this carbon is positively charged, that means this is our carbocation. At the time, only one alkyl group is attached. How many alkyl group? Look at this, only one alkyl group. But in this case, how many alkyl group is present? There are two alkyl group, right? There are two alkyl groups present. So when two alkyl groups are present, dear students, are you listening to me properly? Please give me the feedback. Anybody quickly. Thank you very much. Okay, so look at this one. Thank you very much. Look at this. As it has two alkyl groups, so this is 2 degree carbocation, and you know the stability trend, don't you? We know that the carbocation stability is 3 degree. 3 degree, I cannot write degree, so I am using just 3, 2, 1. I hope you would understand. So 3 degree, 2 degree, and 1 degree. So this is the this is what this is 3 degree, 2 degree, and 1 degree. So this is the order of stability. And why this is happening? Because this alkyl group or methyl group, this is giving positive inductive effect. They are giving what? Positive inductive effect. What is positive inductive effect? They are electron donating group. Methyl groups are electron donating group. What type of group? Electron donating group. So methyl is an electron donating group. Okay, electron donating group. So it gives the electron density towards the carbon center, so this positive charge is spread in a larger region. On the other hand, here we have only one alkyl group, so it is less distributed. The positive charge density is less distributed, and here this positive charge density is distributed in a larger region, so it gives the better stability to this carbocation. As it is more stable, so it gives the reaction more readily. That means with this positive charge, bromine can now come, bromide ion can come, and we can get the product finally. So you understood that if we use this mechanism, I mean, if the carbocation is formed here, at the time it is a 2 degree carbocation, and due to the positive inductive effect given by methyl group, this is more stable compared to 1 degree carbocation formed as an intermediate when a positive charge is built up here, right? Okay, so you understood why it is the major product. So 2 degree carbocation is leading towards this major product, and 1 degree carbocation is leading towards the minor product. Okay, let's go back to this diagram once again. Okay, look at this one. There are a couple of other reactions. Today I will take 5 more minutes. 5 minutes are left in my meeting. Sorry for the late. Actually, I was on time, but due to some technical errors, I had to restart the meeting. Hope you understood. Anyways, we will finish up this one quickly, as you have a class from 2:45. The next class will begin. So I will end up within 5 minutes, inshallah. Look at this. Here, this is our major product. From this major product, if you add ammonia, now it is halogenoalkane, right? Halogenoalkane will undergo nucleophilic substitution reaction. Halogenoalkane will undergo nucleophilic substitution reaction. So look at this one. In this case, cyanide is our nucleophile, right? And in this case, from ammonia, excess ammonia, when excess ammonia is used, heat under reflux, at the time we will get NH2 as NH2, and here cyanide. So this will replace, these nucleophiles will replace bromine, nothing else. So D and this product, perhaps F, I forgot to write here. So D and F, these two products are found easily, no problem. Then sodium hydroxide, heat under reflux. Now this condition is very, very important. When we are using ethanolic sodium hydroxide, at the time we get elimination reaction, and when we are using aqueous sodium hydroxide, we are getting, I told you earlier that conditions are very, very important in organic chemistry. Conditions are very, very important in organic chemistry. So when you are using aqueous sodium hydroxide, we are getting nucleophilic substitution reaction. As a result, hydroxyl group, that is the nucleophile, hydroxide ion will replace bromide ion. I mean, bromine will be replaced by hydroxide simply. So we are getting an alcohol here, right? On the other hand, when you are using ethanolic sodium hydroxide, heat under reflux, at the time we are getting an elimination reaction. So this bromine, and from any of this carbon atom, from the nearby carbon atom, hydrogen will be removed. Hydrogen will be removed from this carbon atom or from this carbon atom, either from this one or from this one, and at the time we will get a double bond. So hydrogen bromide will be removed, bromine is removed, and here hydrogen is removed. So this carbon will have a free hand, this carbon will have a free hand, so they will make a double bond. So this is how we can get the alkene back. That means we started with the propene, you see, and again by using this route, first we have made halogenoalkane, and then in presence of ethanolic sodium hydroxide, when we carry out heat under reflux, we get this product. We are getting product G, right? Okay, the last one, D, heat under reflux. This is a nitrile, isn't it? This is our propane, this is butane nitrile. In fact, this is butane nitrile. So butane nitrile, here is a nitrile group. This nitrile will be refluxed, heat under reflux, acid hydrolysis, and heat under reflux, acid hydrolysis of this nitrile. You know that acid hydrolysis of this nitrile will form carboxylic acid. What will it form? It will form carboxylic acid. So nitrile is turning into carboxylic acid, CH3CH, CH3COOH. Okay, we have around 2 minutes left. So if you have any question, you can ask me. I can repeat. Did you understand my explanation? Dear students, please respond. I have unmuted all of you. So 1 minute is left. Thank you, Samir Akhtar Mamun, for giving me the feedback. Anybody? If you want to say something, you can raise your hand and you can ask. Okay. Inshallah, I will be discussing the remaining questions in the next class. Question number 4 is partly left and question number 5 is left. I will be discussing this one, and keep revising organic chemistry. Keep revising organic chemistry. Thank you very much. See you on the next class. See you on Sunday in the next class, inshallah. Take care. Allah Hafiz. Walaikum assalam, Tausif. Thank you, Samir Akhtar Mamun. Walaikum assalam.